Every year, the moon moves farther away from the Earth, not by much, about 3.8 centimeters, an inch and a half, roughly the speed your fingernails grow. We know this for certain. Apollo astronauts left panels of mirrors on the lunar surface, and for over 50 years we have been firing lasers at them and timing the light on its way home. The distance now comes back, measured to the millimeter, and the number keeps getting bigger. But here is the part almost nobody mentions. If the moon had always been retreating at the speed we measure today, then just 1.4 billion years ago it would have been sitting inside the Earth. And the moon is more than 4.5 billion years old, which means the escape has not been steady. The rate has changed. Something has been quietly speeding it up and slowing it down across the entire history of our planet, and almost none of that history was written down, except once. 70 million years ago, on a shallow tropical seabed, something was keeping a record, not a telescope, a clam. So, let's go back, let's slow down, and look at what we actually know. The mirrors on the moon are real. There are several of them up there. 3 were placed by astronauts during the American Apollo program, on the missions numbered 11, 14, and 15. 2 more were delivered by Soviet robotic rovers called lunar. And in August of 2023, India's Chandrayaan 3 lander set down a 6th one. But the story of how those mirrors got there is older than the moon landings, and it starts with people who were not even sure it would work. Back in 1962, before anyone had walked on the moon, 2 researchers at the MIT, Louis Smullen and Giorgio Fiocco, pointed a laser at the moon and tried to bounce light straight off its bare surface. It was crude. The pulse was powerful but brief, and the moon's rough grey ground scattered the light in every direction. But faintly, against all odds, some of it came back. Around the same time, a Soviet team at the Crimean Astrophysical Observatory did much the same thing with a laser of their own. On both sides of a divided world, people were firing light at the moon just to see if the moon would answer. The problem was precision. Bouncing light off raw lunar rock gave you a smeared, blurry signal the surface is uneven, so different parts of the beam came back at slightly different times. You could get a rough distance, but not a sharp one. The fix came from a graduate student at Princeton named James Fowler, who had a simple and elegant idea. Don't rely on the rough surface of the moon at all. Put mirrors up there. Purpose-built reflectors designed to send light back exactly the way it came, with almost none of the smearing. If you could place a panel of those on the moon, you could turn a blurry guess into a razor-sharp measurement. 7 years later, that idea rode to the moon in the cargo of Apollo 11. The very first array of mirrors was installed on the 21st of July, 1969, by the crew of Apollo 11. And just a few days later, on the 1st of August, a large telescope at the Lick Observatory caught the returning light for the first time. It worked. A student's idea, carried by a rocket, answered by a beam of light. We had a way to measure the exact distance to another world. The reflectors that followed were not all equal. The array left by Apollo 15 was 3 times the size of the 2 earlier ones. And for the first quarter century of the experiment, that single larger panel handled roughly 3/4 of all the measurements taken. It was the workhorse. The bigger the mirror, the more of those precious few photons found their way home. The technique itself is almost absurdly delicate. By the time the beam reaches the moon, it has spread out to about 6.5 kilometers wide. Scientists describe the challenge of aiming it as something like using a rifle to hit a moving dime 3 kilometers away. And yet, by 2009, the measurement had become so refined that the distance to the moon could be pinned down to the millimeter. On average, the center of the Earth and the center of the moon sit about 385,000 kilometers apart. And the reflectors tell us that this gap is opening. The moon is drifting away from us at a rate of about 3.8 centimeters every year, roughly the width of an inch and a half, about the speed at which your fingernails grow. Now, that sounds small. And on the scale of a human life, it is. Nobody has ever looked up and noticed the moon getting smaller in the sky. Your grandparents saw the same moon you see. But the universe does not work on the scale of a human life. It works on the scale of millions and billions of years. And on that scale, 1.5 inches per year is not nothing. It is a story. A very long story, running underneath everything, that almost no one thinks to ask about. To read that story, you would need a witness. Something that was alive and paying attention, not last year, not 1,000 years ago, but tens of millions of years ago. Something that wrote down what it saw and kept the record safe until we were ready to find it. That witness was not a person. It was not a machine. It was a clam. And the man who learned to read it is a geochemist named Niels de Winter, who works at the Free University of Brussels. When he first held the data in his hands, a full day of the deep past laid out in front of him, hour by hour, he did not reach for careful, professional language. He said it was pretty amazing. He said that, basically, they could now look at a single day from 70 million years ago. That is the quiet excitement at the heart of this whole story. Not a telescope, not a rocket. A man in a laboratory, realizing that a dead animal had been keeping a diary the entire time. So let's talk about the clam. It belonged to a family of creatures called rudists. And rudists are strange enough that it's worth stopping on them, because there is nothing alive today that is quite like them. They were mollusks, distant relatives of the clams and oysters we know now, but they did not look the way you would picture a clam. This particular species, called Torretes sanchezi, looked something like a tall pint glass, with a lid on top shaped a little like a bear claw pastry. It had 2 shells that met at a hinge, and it grew crowded together with thousands of others in dense reefs, the way oysters do. Here is what makes rudists important. In their time, they were not a minor detail on the seafloor. They were the reef. In the warm, shallow, tropical waters of the late Cretaceous, rudists like this one took on the job that corals do for us today. They built the reefs. They shaped the shallow seas of an entire era. And then they vanished. They disappeared in the same event that wiped out the non-avian dinosaurs 66 million years ago. Whatever ended that world ended them too, completely, leaving no close living relatives behind. And they belonged to a much larger lost world. The rudist reefs of that age fringed a vast ancient sea, and their fossilized shells turn up today in places that are now bone dry and far from any coast in the Alps and across the Arabian Peninsula, on what were once shallow, sunlit platforms at the edge of a great ocean that spread all the way from the Americas to China. That ocean is gone now. The reefs were lifted up, folded into mountains, and stranded in the middle of continents. But the shells kept their shape. The particular shell that De Winter's team studied had a long journey to reach them. It lived for more than 9 years on a warm, shallow seabed somewhere in the tropics. Today, that exact spot is not underwater at all. It is dry land high up in the mountains of Oman. The sea that clam lived in is gone. The mountains it now rests in did not exist when it was alive, but the shell remained. This was deep in the stretch of time we call the Cretaceous, a period that ran, very roughly, from around 145 million years ago down to about 65 million years ago. An enormous window. And for much of it, in the warm shallows, the rudists ruled. Now, why does an old shell tell us anything about time? Because rudists grew fast. And as they grew, they laid down thin layers of new shell, not once a year, like the rings of a tree, but once a day. Every single day of that animal's life, it added another fine layer of material. Scientists call these layers laminae. Stack up those daily layers, and you have a calendar. Count the days between 1 year and the next, and you are no longer guessing about the ancient past. You are counting it, 1 day at a time. But there was a problem. These daily layers are unbelievably thin, only about 40 millionths of a meter across. far too fine and too crowded to count reliably by simply staring through a microscope. For a long time, that was the limit. The diary existed, but no one could turn its pages without smudging them. So De Winter's team did something clever. They used a laser. They focused a laser onto the shell and burned tiny holes into it, each one only 10 millionths of a meter wide, about as wide as a single red blood cell. And as the laser cut, it read the chemistry inside each layer, the trace elements locked into the shell, which record the temperature and the conditions of the water on the exact day that layer formed. For the first time, they could see not just the years and not just the days, but the changes within a single day. 4 to 5 separate data points inside one 24-hour period from 70 million years ago. They counted the layers, and when they counted how many daily layers the clam had laid down in a single year, they did not get 365. They got 372. Sit with that number for a moment. 70 million years ago, back when this clam was alive and dinosaurs were walking the shorelines, the Earth did not spin 365 times per year. It spun 372 times. There were 7 extra days in every single year. Not because the year was longer. The year was exactly the same length it is now. The Earth took just as long to travel once around the Sun. The days were shorter. Back then, a single day, one sunrise to the next, lasted about 23 hours and 31 minutes, roughly half an hour shorter than the day you are living in right now. The Earth was simply spinning faster on its axis, turning a little quicker, packing a few more days into the same trip around the Sun. And that one fact, a clam that counted 7 extra days, is the loose thread. Pull on it, and the whole story of the Moon starts to unwind. So how does a spinning planet connect to a departing moon? The answer is tides. And to understand it, we have to be careful, because it is one of those ideas that sounds simple but hides something surprising underneath. Start with what you already know. The moon's gravity pulls on the Earth's oceans. As the Earth rotates, that pull creates the tides, the daily rise and fall of the sea. This is ordinary. You can watch it happen at any beach. But the water does not slide across the Earth for free. It drags. As the tides move, they rub against the ocean floor and against the shape of the coastlines, and that rubbing creates friction. And friction, always and everywhere, slows things down. So the tides act like a brake, a gentle, constant brake on the Earth's rotation. Every day, the planet spins just slightly slower than it did before. This is why the days are getting longer, why the clam's day was shorter than ours, and why some far future day will be longer than today. Now here is the part that is easy to miss, the part that turns this from a simple story into a strange one. The energy does not just disappear when the Earth slows down. Energy is never destroyed. It has to go somewhere, and where it goes is into the moon. The same tidal pull that drags on the Earth also gives the moon a tiny nudge forward, speeding it up ever so slightly in its orbit. And when you speed up an orbiting object, it does not circle in tighter, it drifts outward. It climbs to a higher, wider orbit. So the two things are locked together, two halves of one process. As the Earth's spin slows down, the moon moves farther away. The planet loses a little of its rotation, and the moon gains a little distance. They are trading. Slowly, across the ages, the Earth is handing its spin to the moon, and the moon is spending it on getting away. This is not a theory that lives only in equations. This is exactly what the two records show us, side by side. The lasers and the mirrors on the moon show us the moon moving away today. And the clam, 70 million years ago, shows us the Earth spinning faster back then, which is precisely what you would expect if this trade has been going on the whole time. Two completely different witnesses, a panel of mirrors on the moon and a fossil in a mountain in Oman, both telling the same story from opposite ends of time. And there is one more detail hidden in that clam's shell, one that shows just how deep the diary goes. The daily layers were not all the same. They came in bundles. The team found the layers grouped into sets of roughly 14 and roughly 28, and those numbers are not random. They match the rhythm of the tides, the fortnightly cycle, and the monthly cycle that the moon still drives in our oceans today. The clam had not just recorded the length of its days, it had recorded the pull of the moon itself, written into its shell, one tide at a time. I want you to hold on to something here, because it matters later. Everything we have just described, the whole beautiful chain of spin and tide and retreat, is built on a single clam, one animal. 9 years of one creature's life, on one seabed, on one small stretch of an ancient ocean. It is a single frozen frame, pulled out of a film that is billions of years long, and a single frame can only tell you so much. But before we leave the clam behind, there is one more thing. It recorded something that had almost nothing to do with the moon, and yet turned out to matter for the whole measurement. When De Winter's team read the chemistry inside those daily layers, they expected the biggest changes to happen between the seasons, summer to winter, warm water to cool water. That is what you would guess. Instead, they found the opposite. The chemistry of the shell changed more over the course of a single day than it did across an entire year. The daily swing was bigger than the seasonal swing. That was strange. And the more they looked, the stranger it got. The shell grew faster during the day than it did at night. Not a little faster, noticeably faster. As if the animal came alive when the sun was up and slowed almost to a stop in the dark. There is really only one good explanation for that. This clam was not feeding the way a modern clam does, by quietly filtering food out of the water. This clam was farming sunlight. Living inside its shell, most likely, were tiny organisms, symbiotic algae, that survived on light and shared what they made with their host. We see the same partnership today in giant clams, which carry sunlight-eating algae inside their bodies and depend on the day to feed. The rudist, it seems, did the same thing. When the sun rose, its hidden gardeners went to work, and the shell grew. When the sun set, they stopped, and so did it. That is why the shell recorded the day-night cycle so sharply. It was not just marking time, it was living by the light. Now, here is where the story gets human. For decades, some scientists had suspected that certain rudists might have carried these sunlight-eating partners. It would explain how they grew so large and how they built such enormous reefs. But suspecting a thing is not proving it. And one of the people who knew that best was a retired paleobiologist named Peter Skelton, a specialist in rudists who had spent a career studying these very animals. Skelton was blunt about the state of the evidence. As he put it, every earlier argument for sunlight farming in rudists had been essentially speculative, based on the shape of the shells, on suggestive hints, on educated guesses. And in some cases, he said, those older arguments had been demonstrably wrong. People had wanted it to be true. Wanting had gotten ahead of proving. So, when De Winter's shell came along, with its daily rhythm written cleanly into the chemistry, Skelton did not wave it through. He recognized it for what it was, the first time anyone had provided convincing evidence for the idea, rather than just a hopeful story. But he also drew a careful line around it. This evidence, he cautioned, was specific to this one kind of rudist. It did not automatically mean every rudist that ever lived was farming sunlight. One clam proved one thing. It did not prove everything. That caution is not a small detail. It is the entire spirit of how this science works. A beautiful result is not a finished result. Even the person most delighted to see rudists vindicated was the first to say, "Careful now, this shows us this, and only this, and here is where our knowledge ends." And why does any of it matter for the moon? Because if the clam grew by the light, then its daily layers are tied directly to the rising and setting of the sun. The layers are days, real solar days, sunrise to sunrise, not some other rhythm we might have confused them with. The sunlight farming, in a strange way, is what makes the calendar trustworthy. The thing that fed the clam is the thing that lets us count its days. There was one more surprise buried in the temperatures. The chemistry of the shell suggested that the seas this animal lived in were not just warm, they were hot. In the height of summer, the water may have reached around 40 degrees Celsius, 104 degrees Fahrenheit, and even in winter it stayed above 30 degrees, close to 90 in the old scale. Those summer temperatures were pushing right up against the limits of what a mollusk's body can physically survive. The days were shorter, the year was longer, the moon hung closer and larger in the sky, and the shallow tropical ocean was very nearly too hot to live in. That is the world the clam remembered, not a gentle prehistoric paradise. A faster spinning, hotter, stranger Earth, with a nearer moon dragging bigger tides across a boiling sea. Now, let's run the numbers backward, because this is where the story turns genuinely unsettling. If the moon is moving away at about 3.8 centimeters per year today, the obvious question is, what if it always moved at that speed? What if we just take that rate and rewind it all the way back? So scientists did exactly that. They took the current speed of retreat and calculated backward, running the clock in reverse to see where the moon used to be. And the answer they got was impossible. If the moon had always been drifting away at today's rate, then only about 1.4 billion years ago, the moon would not have been orbiting the Earth at all. It would have been inside the Earth. Let that sit for a second. Not close to the Earth, not skimming the atmosphere, inside it, occupying the same space as our planet. A physical impossibility, a contradiction that cannot have happened. And we know it cannot have happened because we have very good reasons to believe the moon is far, far older than 1.4 billion years. The best evidence we have says the moon was born more than 4.5 billion years ago, most likely in the aftermath of a colossal collision when a young Earth was struck by another world, a wandering protoplanet that scientists have named Theia. Out of the debris of that impact, the moon came together. So the moon has been with us for over 4.5 billion years. And yet the simple math says it should have been sitting inside the Earth just 1.5 billion years ago. Both of those things cannot be true. The only way to resolve the contradiction is this. The moon has not always been moving away at today's speed. The rate has changed over time. In the deep past, the moon must have been retreating much more slowly than it is now. The gentle trade between spin and distance was not always running at the same pace. It sped up and slowed down across the ages in ways we are still trying to understand. Which means the clam, as astonishing as it is, has a limit. It gives us one clean, trustworthy snapshot at 70 million years. But 70 million years in the life of the moon is almost nothing. It is a blink. It is the last frame of a film that started billions of years earlier, and everything before that frame is in the dark. To see further back, we needed a different kind of witness, not a clam. Something older, something that could survive not tens of millions of years, but thousands of millions of years. The deeper witnesses turned out to be written not in shell, but in stone. There is a way for the sky to leave its fingerprints in rock. It works like this. The Earth does not travel around the sun in a perfectly steady way. Its orbit slowly stretches and relaxes. Its axis tilts back and forth, and the whole planet wobbles like a spinning top that is very slightly off balance. These slow, regular movements are called the Milankovitch cycles, named after the scientist who worked them out. These cycles change how much sunlight falls on different parts of the Earth and when, and over thousands of years, that changing sunlight changes the climate, shifting the winds, the rains, the patterns of the sea. Layer by layer, those climate shifts get recorded in the sediment settling on the ocean floor. The rock ends up striped with the rhythm of the sky. Here is why that matters for the moon. Some of those cycles depend on how fast the Earth spins and how far away the moon is. As the moon retreats and the Earth's spin slows, the timing of the wobble changes. So if you can find ancient layered rock and count the rhythm frozen inside it, and date that rock precisely, you can work backward to the length of the day and the distance to the moon at the moment those layers formed. One such record comes from rocks in North China that are about 1.4 billion years old. Another, even older and even more remarkable, comes from a formation in the mountains of northwestern Australia called the Joffre Member, a banded iron formation laid down when the Earth was young and the air had barely any oxygen in it at all. Cover that one carefully because it reaches almost unimaginably far back. The Australian rocks are about 2.5 billion years old. And when scientists counted the sky's rhythm inside them and checked it against the precise age of the stone, they were able to reconstruct the Earth and the Moon as they were back then. The result was a different world. 2.5 billion years ago, a day on Earth was not 24 hours. It was not even the 23.5 hours of the dinosaur age. It was only about 16 hours and 54 minutes long. The Earth was whipping around on its axis, spinning far faster than it does now, and the short days blurred one into the next. And the Moon was much closer. The rocks put it at a distance of around 321,000 kilometers, tens of thousands of kilometers nearer than it hangs today. A larger moon in the sky, above a faster world, watching over an ocean with no fish in it and a sky with no oxygen worth breathing. I will not walk you through every ancient record one by one because they follow the same pattern, and the pattern is what matters. Find a rock that trapped the rhythm of the sky, count the cycles, date the stone, and read off the distance to the moon. Do it again with a different rock from a different age, and you get another point on the map. Rock after rock, each one a single lantern lit in the darkness of deep time. And when you gather all those points together, the clam at 70 million years, the Chinese rocks at 1.4 billion, the Australian rocks at 2.5 billion, a shape begins to appear. A long, slow curve of the moon climbing away from the Earth across the entire history of the planet. Faster in some eras, slower in others. Never quite steady. But between those points, there are enormous gaps. Vast stretches of time where we have no witness at all. And the moon spent those stretches doing exactly what it is doing now. At the beach, tonight, pulling on the water, dragging on the spin, and inching away with no one and nothing to write it down. Before we step back to take in the whole picture, it's worth pausing on the strange details, the odd little findings that came out of watching the moon this closely for this long. Because measuring one thing to the millimeter, year after year, tends to turn up things you were not looking for. Start with the mirrors themselves. They are not all aging the same way. The Soviet rovers, Lunokhod 1 and Lunokhod 2, each carried a reflector, and the two were built to the same design. You would expect them to behave the same. They don't. Over the years, Lunokhod 2's reflector faded badly, growing far weaker than it once was, while Lunokhod 1's reflector held up much better, staying relatively strong. Same design, same moon, very different fates. Why one degraded so much faster than its twin is a genuine little mystery, sitting quietly on the lunar surface. And Lunokhod 1 has a stranger history still. For decades, its exact location on the moon was simply lost. We knew roughly where the rover was, but not well enough to hit it with a laser. Then, in 2010, an orbiting spacecraft photographed the surface in fine detail and finally spotted it. Within weeks, scientists on Earth were bouncing light off a reflector that had been sitting there, unreachable for a generation, and pinning its position down from a vague guess to a matter of centimeters. A machine that had been effectively invisible for 40 years suddenly rejoined the experiment. Then there is the rate of retreat itself. That 1.5 inches per year, the speed at which the moon is leaving, has actually been described by scientists as anomalously high. It is a little faster than you might expect, and we already know why it cannot be the whole story. If the moon had truly always retreated this quickly, the impossible math from before kicks in, and the moon ends up inside the Earth far too recently. The present-day speed is, in a sense, a clue that something about our particular moment is unusual. And the reflectors have revealed things that have nothing to do with distance at all. By watching, with laser precision, the tiny way the moon rocks and wobbles as it orbits, scientists worked out something about its hidden insides, that the moon most likely has a liquid core, taking up roughly a fifth of its radius. We reached inside the moon without ever touching it, just by measuring how light came back. The same measurements have even been used to test our deepest ideas about gravity itself, Einstein's theory of how mass and space and time fit together. So far, the moon's orbit has matched the predictions of that theory to within the accuracy of the lasers. Every time the beam returns, it is quietly confirming that our picture of gravity holds, all the way out there. All of that, the mismatched mirrors, the lost and found rover, the surprisingly quick retreat, the liquid heart of the moon, the test of Einstein, came out of one simple, patient act: firing light at a reflector and timing how long it took to come home. Let's put all of this against something you can actually feel, because the numbers only mean something when you can stand next to them. Think about the day, your day, 24 hours. It feels like a fixed thing, the most reliable number in your life. The sun comes up, the sun goes down, and it always takes the same amount of time. But it doesn't. It never has. Go back to the dinosaurs, 70 million years ago, and you would lose about half an hour off every day. Go back to those ancient shallow seas even further, and older evidence from fossil corals suggests that around 400 million years ago, there were a little more than 400 days in a single year. Go back to the young Earth of the Australian rocks, and the day shrinks to barely 16 hours. The number you trust most is not a constant at all. It is a slowly moving thing, and the moon has its hand on the dial. Now think about the moon in the sky. It looks permanent. It looks like it has always been exactly there, exactly that size. But there is a hard limit on how close the moon could ever have been to us, a boundary written into the laws of gravity. It is called the Roche limit. Come inside that boundary, and the Earth's gravity would overwhelm the moon's own gravity and tear the moon apart into pieces. For the Earth and the moon, that boundary sits at about 9,500 kilometers. Compare that to where the moon is now, about 385,000 kilometers away. The moon today sits at more than 40 times that shredding distance. It is safe, it is far. But in the deep past, it was closer to that edge than we would ever want to imagine. A young moon, enormous in the sky, hanging just a few of its own diameters above a boiling ocean. And there is one more subtlety worth appreciating, because it shows how carefully this had to be done. When we say the clam recorded a day, we have to be precise about which day we mean. There is the solar day, the time from one sunrise to the next, which today is almost exactly 24 hours. And there is the lunar day, the rhythm set by the moon's position, which right now is a little longer, closer to 24 hours and 50 minutes. They are not the same. They drift apart by a small but real amount. The whole reconstruction depends on knowing that the clam's layers followed the sun and not the moon, that they marked true solar days. That is exactly why the sunlight farming discovery mattered so much. It told the scientists which clock the clam was keeping. Get that wrong, and every number after it bends. Get it right, and the calendar holds. And here is the comparison that reframes everything. We tend to think of the Earth and the moon as two separate things. A planet and its satellite, fixed, finished, done. But that is not what the evidence describes. The evidence describes a relationship. A long, slow, 4.5 billion year exchange between two bodies that have never once stopped moving with respect to each other. The Earth gives away its spin. The moon takes the distance. The tides rise, the friction bites, the day lengthens by a fraction, and the moon climbs a little higher. It has been happening every single day, without pause, since before there was life on land to see it. The clam saw one day of it, the Australian rocks saw another, and the green laser leaving the telescope dome tonight is watching it happen in real time. We are not looking at a finished picture. We are looking at a single moment in a motion so slow that a human lifetime cannot register it, and so old that it predates almost everything. So, where does that leave us? We know the moon is moving away. That part is not in doubt. The mirrors on the moon and the returning light measured down to the millimeter have shown us the retreat directly. About 1.5 inches a year, patient and unstopping. We know it has been happening for a very long time. The clam in the Omani mountains gave us a clean, trustworthy page from 70 million years ago, counted day by day, 7 extra days folded into every ancient year. And we know the retreat was not always this fast, because if it had been, the simple math puts the moon inside the Earth at a date the moon is far too old to allow. So the rate has changed and shifted and wandered across time in ways the deep records are only beginning to reveal. But look at what we still do not know. We do not know the shape of the curve between the lanterns. We have a point at 70 million years, and a point at 1.5 billion, and a point at 2.5 billion, and between them and before them, there is mostly darkness. We do not know exactly how far away the moon was 100 million years ago, or 500 million, or 1 billion, with the confidence we would like. We do not fully understand why the retreat sped up and slowed down when it did. We are holding a handful of frames from a film that ran for 4.5 billion years and trying to guess the story in between. And the people who found these clues are not finished. The scientists who read the clam are already searching for older shells, older fossils, older stone, hoping to catch more snapshots, deeper in time, to light a few more lanterns in the dark stretches of the record. Because that is how this works. The clam did not close the question, it cracked it open. It answered how fast the Earth spun on one ancient day, and in doing so, it asked us 10 new questions about all the days we still cannot see. Tonight, the moon is a little farther away than it was when you were born. Tomorrow, it will be farther still. Not enough for you to ever notice. Not enough to change a single thing about your life. But real. Measured. Confirmed by light that traveled to another world and came back to tell us. We built the mirrors. We fired the beam. We caught the few faint photons that survived the trip home, and from them we learned that the oldest, steadiest companion in our sky has been quietly, gently letting go of us the entire time, and that a dead clam in a mountain in Oman remembered a day we were not there to see, and kept it safe, and waited for someone with a laser to finally ask. The moon is leaving. It always has been. And we are only now, after 4.5 billion years, learning how to watch it go.